Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Ding dong. Good morning, everybody. Welcome. As many of you know, Microsoft and Intel are funding something called the UPCRCs, which means Universal Parallel Computing Research Centers at the University of Berkeley and at the University of Urbana-Champaign. Today we have the great honor of having 5 visitors from Berkeley who will be visiting several teams in incubation, products, and research. And the visit starts with this presentation. The presentation will start with David Patterson giving us an introduction of the center, followed by Kurt, followed by John, followed by Russ. Thank you.
Turn on. Okay, nice to see everybody again. I'll be here. I was here last month. I'll be here next month. I don't know about July. It seems like I'm probably going to be here. Maybe I guess. Give you an overview of this lab. It started 2.5 years ago. We were really driven by applications, which is rare for a lot of computer science projects. And what we pitched in the proposal that Intel and Microsoft selected were the applications in black. And we've enjoyed the applications influence so much we've expanded them to these new ones that are shown in blue. And Kurt's going to be talking about patterns in these applications right after me. I'm going to talk about some of our big bets. One of our big bets is that the way to make parallel software is to have a really good software architecture. And so in our old Berkeley View report, we talked about these 12 or 13 dwarfs, or motifs we called them. And we call those the computational patterns, which are shown on the right. And then in the process of doing the research, decided that these programming patterns that are good for any kind of program will be the key to us being able to get parallel software. In particular, that software should have as its architecture a composition of these patterns on the left. This has been captured in something that's called our pattern language, and Kurt's going to talk about this. This is happening with people here and at Illinois and at Intel. Our mantra has been, and I would say this is, other people say this now too, is we see the world as productivity level programmers and efficiency level programmers. So domain experts as examples of productivity level programmers, programming something like Python or Ruby, or in the efficiency level language programmers, a lot of people, like people here, are the C#, C++ types of programmers that are aiming for this bare level efficiency, where the domain experts would be happy with pretty good speed up and productivity. And so we struggled with this a lot. In fact, if you were to read our proposal, the productivity level thing was kind of as a hole in our proposal. We should do something about this. We didn't really know what to do. We were kind of afraid that we're going to have to invent our own programming language, or that was the only viable way forward, because the chances of inventing a programming language and it actually catching on would seem 0, but we didn't know what to do. And now we have a story, and I'll tell you about that. So one of the things we wanted to do was to make efficiency programmers productive. And we and many people believe auto-tuning is a better way to do code generation than simply traditional static compiling. Looking at a specific example on the right in the stacked bar graph is increase the number of threads. The auto-tuning part is that red part there. So there's significant speed-ups of auto-tuning by generating code and seeing what runs well on a particular computer rather than figuring out just the compile time. Problem with that has been is it takes really smart people who know architecture and the algorithms to pull that off and kind of use up one grad student at a time. So we've been trying to see what we can do about that. We won't tell you about our successful use of machine learning. There's been some breakthroughs by members of the team on how to avoid computation, and even things that have been around forever like dense matrices. We made big improvements in that, but I will talk about CJITs on that. CJITs is this new idea that wasn't in the proposal And I think of it as making productivity programmers efficient. Or you can think of it, if you know what autotuning is autotuning with high-order functions. So rather than invent our own programming language to help productivity programmers, we would pick one that's already productive, like Python, say. Now, these modern scripting languages like Python really are sophisticated languages that have all the powerful features that you would like to see in a programming language. And so the acronym comes from that this infrastructure is going to specialize the computation, but it's not going to have to take any Python program. It's going to selectively do it a function at a time. We will have the option of doing just-in-time compiling to create efficiency-level language code. And then the other part of selective embedded is it's really you write this thing in the language itself, and you can use the standard interpreter. You don't have to modify it or anything like that. So to try and get the name here, so if we're writing in Python, here's these Python methods. A couple of them are marked as, this would be interesting to go faster, the G and the H one. Because it's standard Python, if you don't have a specializer for it, it just gets interpreted as it is before. How do you mark them? Well, maybe the programmer marks them, or maybe you monitor the performance and see which one takes a lot of time. The H does have the CGIS mechanism, so it gets invoked. There's a specializer for that hardware, and then that invokes the system on the tribe. So the selective part of the name, embedded, that it's actually written in Python, that's indicating those pieces are in blue. We write them in Python and generate the just-in-time compiling, what you see, and then the specialization, get the speed up there. So we're not going to have time to talk about that, but Armando Fox, right here, is leading the charge on that effort, and he can ask questions about it, and we're pretty excited about it. And recently, we think not only will it help with multi-core or many-core, we think it could help with cloud computing as well. So some of the same arguments there, and Armando can tell you about that. We have a big effort in correctness, debugging, verification, as does Microsoft. And this is led by Koushik Sen, who was an intern here many years ago. Koushik seems to be winning all the awards in the project, as far as I can tell. He's won several Best Paper awards. There's this research highlights of the new communications of the ACM. It's got selected for that, so that's almost like yet another award. He has these really interesting ideas at the intersection of testing and debugging, which people here have done as well. Active testing. So the idea of the productivity layer, we're going to try not to let people specify some of these problems that can really be hairy to debug. But at the efficiency layer, we can't avoid that. And Koushik has developed techniques that have worked extremely well even on popular open source software and cover previously unknown bugs, and which has led to a lot of these awards. And Ross can answer questions about correctness and debugging. Kubi will talk about our operating systems effort. A lot of the emphasis is on isolation and quality of service is what we're after. Oh, I left off Burton's. So Burton Smith said, oh, hi, Dave. How you doing? In my fall visits, my fall tour to Microsoft, he said, by the way, I've solved the resource allocation problem. I can't tell you about it because I'm filing a patent, but I've solved it. Okay. So, okay, that's interesting. We'd like to hear it when he can. So he came this month. He came in April. He came on April Fool's Day. Yeah, it wasn't a joke. He actually claims to have made big progress on it, and we're implementing that, or going to implement it right now to help us with the quality of service. We've also got some ideas of how to make parallel libraries work well together. Often the libraries assume that no one else has got the machine but me, and then they can be scheduled, and our Lithe system does that, and Kubi can tell you about that as well. Closer to what I know about, we think one of the problems in architecture is that people use software simulators, and it's so, when you're having scores or hundreds of cores, it just takes forever, and so you can't run very much. And I think the architecture community is kind of bottlenecked in how much they can simulate to make progress on many core. We and others, particularly Chuck Thacker here, are betting on FPGAs. Our version of it is a simulator that it does 64 cores on a very inexpensive board, which was a big advantage for us. As the students were running out of time, they just used their credit card and got some more. This version runs 250 times faster. So what does 250 times faster mean? That means students can get a result in an hour versus 10 days. And when it's it makes it clear that research is latency oriented, right? You want to try this experiment to see if it works or not, the parameters are right. Getting the answer back in an hour versus waiting 10 days is completely different. The stress level changed, the rate at which we can do research. And we were very proud that last January at our research retreat, we were able to do a demo that tied all these pieces together. In summing up, this really is an integrated research project. It's often difficult when you're not in academia to tell the difference between a facade and a real integrated project. This is a real integrated project. All these pieces are working together. We all sit with each other. We all interact. And it's paying off. I'm surprised at how much progress we've made. This is a really hard problem, right? All these companies have gone out of business trying to solve. We've made a lot of progress in 2 years, and I'm surprised. We've got some visibility besides covers of the ACM. We do a boot camp. So far, we're doubling every year, and so we're going to bigger rooms where we invite everybody to come and hear our versions of the ideas. There's a hot par that's associated, it's a Usenix workshop, but it's at the Berkeley campus that we're involved in. Kurt's been leading this way on the Paraplops patterns workshop, and there's a wide following of his language. And people really are coming, amazingly, all over the world to say, I've got a problem. Kurt, show me how to parallelize it, and he does. And they get speed up, and we're even planning on testing this idea on undergraduates with Kurt's going to lead the class this fall. And that's the overview. I presume there's not going to be any questions. It'd be great if there are questions, but I bet there aren't. It's too early in the morning. So Kurt, I will pass it on. I thought saying there wouldn't be any questions would get you guys to.
Sometimes that works.
Sometimes that works.
Okay, am I live? No. Microphone?
Did you turn it on?
I've got a little green light here. I'm on. Okay, cool. Okay, so I run a group within ParLab called the Palace Group, which has one of those kind of megalomaniacal acronyms. We're looking at applications, libraries, languages, algorithms, and systems. And what we're kind of motivated by are these new mini-core chips. We don't see the Intel folks putting up the Larrabee slide as often as they used to, so that worries me a little. But you can go out and buy one of these today. So you've got, depending on how you count them, at least 16 or as many as 512 processors, depending on how you look at it. So we can build them, but the question is, how do we program them? In particular, how do we program them to do stuff that we're really interested in? Not just stuff that to demos the particular machines, but that we're really interested in. And so my feeling is that the future microprocessors will be really limited by what we can program. So I'm going to start out by telling you how I think you should not parallel program. So you take your code, you profile it, you look at that preference profile, scratch your head for a while, you go, oh, well, I can add some more threads here, iterate through this loop until you think it's fast enough at least, and you ship it. And the problem with that approach, first of all, this is not something that academics just sit around and kind of put up as a straw man and knock over for fun. I mean, this is if you, my friends at Intel, if you buy enough parts, they'll ship an application engineer over to help you parallelize your code. And this is more or less exactly what they'll tell you to do today. And the problem with that, it's not that it's kind of just aesthetically unpleasing somehow, is that there are lots of failures, and there's lots and lots of times for any of you who actually tried this that at the end, software running on end processor cores is actually slower than software running on just one. So if we look at, well, why is that? Well, let's think about what this person is thinking about when they go through that inner loop and go, let's see, I need to recode this with more threads, right? So there are books out there. They start looking at locks, threads, semaphores. They do UML sequence diagrams, try and puzzle through this a while. And I don't know if any of you have tried that, but after a while you start looking at something like this. The mood is kind of anxious and depressed here. And one of our colleagues at Berkeley, Edward Lee, has actually written a very good paper kind of analyzing some of the problems with coding with kind of a thread mentality. So what's the alternative? Well, the methodology that we're pushing is it's a similar loop, and there's a human in the middle. So in that regard, it's not so different. But what we're thinking about is, what we're focusing on is actually architecting the software to identify parallelism, not just merely jumping in and find threads. And so we spent a lot of time on architecture, And then today it's really a thought experiment. Let's see, how does that software architecture map onto the hardware architecture? You write up some code, you do some performance profile. You go through this same loop, but in the inner loop of this, we're rethinking the architecture. We're not just trying to code in a few more threads. So why is that different? Well, this person, what are they thinking about when they say re-architect with patterns? Well, today code is serial. That's a fact. But the world is parallel. So there's a sense that if we really dig deep into the application, we really understand it, then we will find the parallelism. And then we just need to reflect that in the software. And so what that person is thinking about is like computational patterns. I'll show you in a moment. I guess Dave showed you as well. Structural patterns in general software architecture. And you look at this individual. That looks like a well-adjusted, happy individual to me there, kind of contemplating his architecture. Okay, so Dave flashed this slide. So I'm sure all of you have heard about patterns. Patterns have been around and popular, I think, for about 15 years now, at least. What's different about our endeavor, called R Pattern Language, which coordinates with work of Tim Mattson, Pattern Language for Parallel Programming, is that we're trying to do an entire pattern language, which means we're trying to do a set of patterns which will take you all the way from an application all the way down to a detailed implementation. Now, it's not that adding some patterns at, say, any layer of this is not a useful thing to do. It's just it's not quite as aggressive or as comprehensive as what we're trying to do, which is kind of soup to nuts. You start out with an application, and going through the pattern language, you'll end up with a detailed implementation. So I don't have time to talk through all this, but I did want to go in a little more detail at the top level here, these structural and computational patterns. And so the structural patterns are, if you look at those, go, wait a minute, I've seen those before. Those are the Garland and Shaw architectural styles with maybe a few additions like MapReduce and iterator pattern here and so forth. But these basically define how you structure your software, but they don't tell you anything about what's actually computed. And although I've used in teaching software engineering in general this analogy that software is like a building, finally after a long time it occurred to me, software is actually a lot more like a factory, and in that regard these structural patterns are about how you actually lay out, say, your factory plant. So complementing those are the key computations. Now, this I think is more uniquely the ParLab contribution, which is we in ParLab, long before the Intel and Microsoft UPCRCs were even a gleam in anyone's eye, Dave, Krista Senich and I, Ross, Kubi and so forth would get together on Tuesday afternoons, and we would look at different application areas. Sometimes we'd look at individual applications. Sometimes we look very broadly across application areas like high-performance computing or computer design of integrated circuits or embedded. And we would look across and basically ask ourselves the question, what are the core computations that are performed in those application areas? So this wasn't exactly drafted overnight. We did jumpstart on Phil Cole's observation that he had identified 7 classes of computation which were broadly used in high-performance computing. So red here means highly used. Orange means somewhat used, green less, and blue means probably not so evident at all. And so literally week by week, as we looked at more application areas and slowly added more patterns, we came up with this list here, which in general, my experience now is I'm happy to challenge this audience. I'll be here for 2 days. You bump into me in the hall and say, well, what about this computation? Then if it's not on here, then we'll add it. But I mean, after I guess 3 years now, things have really settled down quite a bit. So these describe computation, and it's interesting for, I think you can maybe relate to in a software audience like this is, it's amazing how little we've actually talked about computation. I mean, we've talked to death about, these architectural styles and object-oriented programming, data hiding, all this stuff. We don't really talk about the core computations as much when we talk about engineering parallel software. And so to me, it's as though we've been talking about the layout of the factories without actually talking about the machinery that goes in here, because these computations are, to me, the actual machinery of the factory. So then when we put those together, it's analogous to the design of an entire manufacturing plant, and this is an entire kind of anatomically correct software architecture, the high-level software architecture of one of our applications, the large vocabulary continuous speech recognition. Now, literally the afternoon that kind of went through my mind, wow, this is really more like a factory, I, honest to God, ran over to our engineering library and said, boy, there must be a lot known about this. And I can't say that in looking at the books and textbooks on factory optimization, I was like blown away by all these novel ideas. But I was very gratified that, wow, they are thinking about the same things like scheduling, latency, throughput, workflow, resource management, capacity. Probably one of the most interesting chapters was what they call work cell design, which essentially gets, what's about the appropriate size of a little work cell, to minimize traffic and so forth like that. There's a long discussion of trade-offs like that. So I think this analogy is holding up well. It helps, at least it helps me think about the problems that we're facing here in software. So the formula that I'm going to show you in the next slides are how we identified particular applications. We worked with domain experts. We typically, with each domain expert, had their state-of-the-art algorithm that they wanted to go faster. We took our tall, skinny parallel programmers, which meant my graduate students, and we architected them, the software, using the patterns I've described, and ran that on parallel hardware, and produced what I think you'll agree are not, modest improvements, yeah, heck of a job, good engineering work, but really game-changing speed-ups, which have the potential to be scalable. So, yeah.
Where do you put an application like Outlook, which seems to be constantly hanging in your list of things? And and Outlook doesn't really run faster if you give it 20 cores. So.
Yeah, so Outlook is kind of an event-driven architecture, or you might kind of put a model view controller around it, and then but then there we'd have to dig in and look at the core computations. But in a lot of these kind of office automation, I mean, there are really various types of graph algorithms sitting there, traversing lists and things like that, and.
When I look at your list of your applications, that by itself doesn't seem to match to one of the columns.
Yeah.
There's a class of those kinds of applications.
That's absolutely true, and I guess this is a good reason to come to Microsoft, is that there's no doubt that office automation type applications have been neglected in our focus. Part of that is because it's not that we're really shying away from large bodies of code, but we are shying away from large bodies of code that we can't get down to some basic kernel, right? So, we'll be around for 2 days, and if you can help me understand, well, if we sped up these particular kernels, by some large amount.
Kernel there, right?
Yeah.
There is a lot of small things here and there that it is really hard to go make use of those things. But,
right.
but many of the applications we have, like, I'm in Visual Studio. Visual Studio has the same problem, is that there isn't like a graph algorithm which runs for 20 hours that you can parallelize.
Right. Well, I don't think this is something that I'm going to mastermind during my talk here, but I'm here for 2 days. I am at your disposal. I'm completely happy to sit down and take a look at those. And also I'll say something a little more, which is, we haven't been shaken up yet. I mean, even things. As soon as we published the view from Berkeley, folks at other universities went around giving talks on Amdahl's law, making remarks that some universities seem to have forgotten Amdahl's law and things like that. And
that was in our Berkeley View report.
Well, no, we mentioned Amdahl's law, but the fact they weren't suddenly doing tutorials on Amdahl's law after 20 years because they just thought, oh, time to get out that tutorial material. People were standing up in front of audiences saying some universities have forgotten Amdahl's law. The fact that we put a line or two. But I'm going to show you a bunch of applications where people thought we would be defeated by Amdahl's law, and we were not. Yes, sir.
It seems like, in general, the focus has been downwards, looking at how to use parallelism in the hardware. And another source of parallelism is in the environment. I mean, you have, in finances, you have streams of data coming in robots, you have sensors giving you streams of activity. In Outlook, you get streams of requests from all sorts of sources, and it seems like there's that aspect of parallelism which is dealing with data streams, asynchrony in the environment, being able to react to that, and in order to be able to react to it quickly, you also need to take advantage of the parallelism in the underlying hardware. So I think a lot of applications actually combine these two. If I'm in games, I'm using GPUs and I'm using multi-core to speed up things, but I've also got to have an architecture that is responsive to network events, to input. With things like Natal, I've got a lot of multimodal. So it seems like you've sliced out a very important part, and it focused more on sort of like you were saying, sort of the kernel. And I think there's a whole set of applications which are, have this external environment and asynchrony that speech recognition a little.
Right. So so first of all, I mean, briefly, and again, if you don't mind, I'd like to. I mean, I'm here for 2 days to talk about the broad-ranging cure for cancer, whatever. Or, what about Zimbabwe, things like that. All that stuff I'm happy to talk about. But what I'd like to do is make sure I get through what we have done.
I mean, you're going to get questions, so I'm sorry. I think it's a very legitimate question.
No,
so
let me address your question.
I'm asking a very specific technical
Okay,
point.
so, all right, then.
So I'd like to hear your thoughts about it.
Sure, okay. So first, I think you have to understand the domain of the problem that we're trying to address, which is there is, for the first time in history, inexpensive parallelism being packaged in parts and put in people's laptops and desktops, and the question is what they're going to do with that. Now I think that's a very relevant question for Microsoft.
That's great. That's great, and I want to have a conversation, and we can have that later, but I think the other trends are these things are networked, the computers are smaller, the disks are huger. So the fact that it's just more processors that we need to leverage is just a small component of a much larger ecosystem that I think you need to track all those things.
Well,
and take them all into
well,
account. Not just about.
So you probably said I'm from Microsoft. Well, I'm from Bell Labs, right? I'll stand up here for 24 hours and discuss this with you if you want.
No,
in the meantime,
take that offline. I'm just saying it's not just about trends in the hardware. It's trends about disk. It's trends about networking.
Yeah, there's obviously a lot of system level trends, and there's a lot of software out there. But I mean, I think if you, at the nexus of that in the world that I live in, is a desktop or laptop, and if that doesn't utilize the processors that are economical, now economical, then all this other stuff is going to be held up by that, right? Okay, so, okay, fair enough is good enough. Okay, so I basically propose this way of how do you parallelize things. And so what I'd like to do is go in a little bit of detail on one application and then just kind of literally, I think at this point, flash at you a bunch of other applications. And so part of this is to show, it's kind of a long-winded way of saying, trust me, we really did some of this. So it's not just the professor talking about, we said we were going to architect these things and then students went off and hacked up code. And part of this is really to get some insight into how this proceeds. So, so this is one of the first things we looked at. Berkeley is a hotbed of machine learning, and support vector machines are at the core of a lot of what we do. Support vector machines basically do a 2-mode classifiers, which is great for like separating out the baby pictures from the flower pictures. And the basic way you approach here, this architecture that I have at the top level here is a pipe and filter architecture. We train on some initial examples. You put in some seed photos of children, you put in some seed photos of flowers, you train your classifier, and then you get some new images, you extract the features, you train them, and you exercise it and get your results. So at the top level here, we have a very simple pipe and filter architecture. As a matter of fact, at the top level of almost any software, you see kind of a series of filters connected by pipes. So we're going to go a little bit deeper on that in this example. So looking at this feature extractor, if we pop open this filter, what we see is another little mini pipe and filter architecture. And if we pop open this filter, we see a little structured grid computation acting over the image. If we pop open this filter, what we see is another what we call a structural pattern, map reduce, which is mapping computations over this. What kind of map computations is it mapping? Dense linear algebra. And then the actual building up of the feature vector, the descriptor, then is a map reduce computation to map another computation on there and gather it all together. And what's being done at each of those maps is a structured grid. So that's going, this is kind of, at this point we'd say, yeah, that's a high level architecture. You've got to turn it on your side. You see kind of a tree structure there. Okay, then if we go into the train classifier, Basically, this is an iterative approach here. So what we're doing here is we're just, on our training data, we're just slowly piecing together a frontier that says basically, these are the babies and these are the flowers. And this is essentially optimization. We're doing that by solving a quadratic programming problem to create the space. And we're iterating over that until all of the points to be classified, or all the original training points are within some margin of error. If we pop open these, so we have an iterator over, we pop open this filter, we have an iterator. Inside of that iterator, we have a simple pipe and filter. Look inside those filters. Again, we have a map reduce. Look inside those maps. We'll see, again, just some dense linear algebra. So finally, the third piece is this exercise in the classifier. So after we've done the training, and we actually have a new photo to classify, so basically what we build a frontier during training, and we've got to evaluate which side of this frontier, is this a flower, is this a baby? And so inside of this exercise in the classifier, we just have a simple pipe and filter where we compute dot products across all the elements which create the frontier of the support vector machine. That's using dense linear algebra, and then sum up and try and decide which side then of this frontier is this on. Okay, so that's really it. Nothing up either sleeve. You can say, well, that's all pretty obvious or not. But by systematically going through this, rather than just jumping in and seeing where's the bottleneck in the support vector machine code we downloaded and so forth, we feel we were able to get a lot more parallelism. And so we published that work a couple years ago now at the International Conference on Machine Learning, and we were able to get about 100x speedups. And if you want to download this and try it yourself, last time we looked, or there were about 900 downloads of this software. Okay, so I'm literally, I think I'm down to like 5 minutes now to go through 7 more applications. So in the interest of just, I presume there are people from different applications groups here, I'm just going to literally flash and reiterate, the message on some of these, and then if you want to talk about speech recognition or computational finance, object recognition, I'll be happy to talk more about that. So again, our approach is we find domain experts, like Jitendra Malik has a strong computer vision group. We look at his state-of-the-art algorithm for detecting contours here. And this is kind of a classic example of the way in which we interacted with other faculty. Great algorithm, best results in the world, runs really slow. So we dug into the architecture of that. This is the top-level architecture, which, as I say, always looks a little bit like pipe and filter. And the moral of the story is we got about 130x speed up of this. We've released the software. It's got about 490 downloads. And this 130x speed up, when I talk about these game-changing speed ups, when Jitendra first came to us, his software, his contour detector was so slow that it was a non-starter for Adobe to even talk to him. By the time we ended, he's saying, okay, well, let's do video, right? At these speeds, we can begin to talk about doing contour detection in video. MRI is a very different. So Professor Lustig, new professor at Berkeley, he had a very fast algorithm for doing compressed sensing of MRI. So he was able to gather the data very quickly, and using this compressed sensing, reducing by estimates of a factor of 4 the amount of MRI time. That's great for UI. For children, that can be really critical, making the difference between anesthetic or not. But the problem is the radiologist needs an image to decide, do we need to do take some more images? So the reconstruction has to be in real time. His reconstruction took hours, right? So it was basically a non-starter for clinical use. So we dug into the architecture of that, getting pipe and filter to the top. Here it's a little easier to see. We were able to find these kind of nice large fork join areas where we could do dense linear algebra across here. Another fork join here, data parallelism across these Fourier transforms and so forth. And we were able then to speed that up about a factor of 100. And so it went from, again, being kind of an interesting academic exercise to something that could actually be employed in clinical use. And it's been in use in over 200 trials now, producing images that radiologists really look at. So those are very dense computational type problems. Speech recognition is very different. So, you have the basic idea of speech recognition. We have voice input. You want to get word sequence out. So there's some signal processing up front. What we focused on, and there's lots of potential for kind of data parallelism up there with the speech processing up front. But what we want to focus on is what we thought was actually the harder problem, which is the inference engine here. So again, here's kind of an approximately anatomically correct high-level architecture of the inference engine, iterating through the individual phones. Here, a little bit more detail on that. And to get some sense of why this is a lot harder, if you dug into those other computations that I kind of flashed up, we really went down to the details of dense linear algebra. You'd see a matrix multiply, things like that. You're not shocked that we can make that run faster on a GPU, right, and so forth. Well, this is a weighted finite state transducer, and so we have the problem, which those of you who tried to parallel graph algorithms notice, is that you never quite know where you're going next, even though you've got a lot of places that you need to go. And once you get there, somebody else may be racing to get there first. And so there's lots of problems with how to parallelize these graph computations. But nevertheless, we were able to speed up a factor of 11 on a mini-core machine. And the interesting kind of, that's 11 is a lot different from, say, 100. But the fact is that we were able to get faster than real time. So if you were trying to, say, do a real-time meeting diarist, on your laptop, you could envision actually being able to do speech recognition of, say, a meeting in real time. Yes, sir?
Speedups ever superlinear?
I'm sorry?
Are the speedups ever superlinear? Do you have more than 11 cores, or?
So it depends. It goes all the way back to that first slides of, whether you say it's 16, whether you say a GPU is 16 processors or 512 or something like that. So if anybody shows you more than 512, something's funny's going on. But we have good scaling, that is to say, you throw more cores at it, we do continuously go faster. But we're not say getting more than 512 speedups. We are getting more than 16 speedups as you've seen. Okay, here's another one, computational finance. So value at risk sounds like a good thing to do, particularly after October 2008 or so. So here's very simple kind of top-level architecture of the 4 steps of Monte Carlo in finance, and we were able to run this 60x faster on a parallel processor, which is still yet to be released from Intel, the Larrabee processor. I think we can say that. Oh, getting recorded. I hope I can say that. This was done during a summer internship. So those are the applications that we have that are kind of tidied up, published, peer review. People seem to be excited about. People want to download the software. I'll just literally flash at you then some other things we're doing, just in case you're interested. So object recognition. So kind of building on the earlier contour detection work, which we described to you earlier. We're looking at this basic problem of you've got some basic categories like swans, bottles, Apple logos, and so forth that you've trained on, and then you have a new image, and you want to be able to identify that image inside of a photo, say. And we've been able to speed up pretty significantly Jitendra Malik's algorithms on both the training portion, 77X, and the classification portion there. So as I said, we got such speed ups on still images that Jitendra, well, why aren't we doing video? So we worked with one of his postdoc, Thomas Brox here, who was looking at this whole issue of how do you follow motion in a video. So we have something like this. We'd like to actually follow the motion of this chameleon walking through here. So again, we architected that out, architected that down until we got to some high data parallelism. And we were able to get a 35x speed up, and to give some tangible sense of what does that really buy you if you actually try to track the motion of somebody moving as fast as, say, a tennis player with that leg extended. Other approaches just won't be able to capture and identify that leg is actually moving continuously with the whole person, but we were able to do that in real time with this. And then last, I just want to clarify, this is not a Berkeley professor and his graduate student. I want to be clear about that, particularly since this is being recorded. And no, it's I have a beard. I had no hair on top like that. Yeah. So in puzzle detection, what you're trying to do is you're trying to identify key features in human beings. So basically, Lubomir, another postdoc of Jitendra Malik, has been working on how we can use unique features of human poses to identify humans quickly. And again, we were able to speed that about 17x. And it's interesting, you know, our work is building on top of each other, and actually the matrix multiply in time in the middle, that support vector machine slides that I showed you earlier is actually the bottleneck in this computation. Okay, so just to wrap up here, so, you know, you can probably guess in this formula that I just showed you earlier, can you see what the bottleneck is? Pretty clear. What's wrong? What's the big limiter in this picture? Yes, sir.
You?
Well, in a roundabout way, you know, but these tall, skinny programmers, right? I mean, basically everything that I've shown you has required 1 to 3 tall, skinny programmers to dig in there and spend a lot of time. So what we really want to do, my students do these speed-ups and architect these applications as kind of an initiation fee. But what we're really doing is using these tall, skinny programmers to build application frameworks so that the domain experts can use these frameworks without having to have some expert programmer there side by side going every step of the way doing the implementation. And so to give you in just a couple slides what this looks like, so I showed you this earlier, this recognition inference engine in the middle of this. And so oftentimes, if you really dig through, you know, C++ code, hopefully not, but, you know, even MATLAB, to try and understand what domain experts are often doing, they're often just doing a wide range of experience about choosing some very high-level parameters. What's the pruning threshold? How do we want to do the observation probability? Do we want to use, how do we actually want to represent the words? Do we want to use weighted finite state transducer? Do we want to do lexical tree and so forth? And so these very high-level decisions that domain experts want to use end up, you know, invoking an awful lot of code when you actually want to experiment with them. And what we're trying to do is package that up in a way that they don't have to do that. So we kind of see 3 different varieties. One is kind of the radio button or bullet point selection menu type, where it's pretty clear the few choices that you want. The other is where they might actually just go in and code a key kernel. And the other is how they might actually take some series of filters on a pipe and filter and do repetitive computation across a number of those, right? So it's just to give you some intuition. Yeah.
I think you're 43 out of 36 slides.
Yeah. No, I'm up now. Yes, sir.
You got 40 minutes left.
Yep. So to conclude, so we're pretty gung-ho about single node parallelism, and we believe that the key here is to start with software architecture, not just jump in coding. And I believe I have a lot more credibility saying this today than I had 2 years ago, because we've actually had some success doing this. In conjunction with domain experts in particular, we've demonstrated this approach in a wide range of areas. So I think also we're, you know, I mean, office automation sounds pretty tough, but, you know, once we got past speech recognition, we weren't afraid of graphs and so forth like that. And the goal here is essentially to encapsulate what we've learned in terms of frameworks that we get in application developers. Okay. Maybe while the next person's setting up, I'll be happy to take some questions. Okay. Yes, sir. Sorry, I had a little trouble hearing you. Oh, great question. Great question. Yeah, thanks. You know, you always love the questions that get you to talk about one more slide, even if I can't show it. Right? So yeah. Well, if you can page up that pattern. Some geometric decomposition, and then you're going into some sort of SPID kind of, and then onto say SIMD implementation. That path is repeated in maybe 70% of the applications that we see, and so we're building essentially not a high-level application framework, but a programming framework that says if you're doing MapReduce of this variety, if you're doing parallel scans, gather these types of computations, then you know, here's a programming framework in which you can do those in a higher level language, and then that goes on to support all the computer vision stuff I can describe and use that. I like that question better than this question. Anything else? Okay, thank you.
Okay, can you hear me? Can you hear me now? Testing? There we go. So my name's John Kubiatowicz, although most people call me Kubi because they can't pronounce my last name, so that's fine. But I'm going to talk a little bit about some of the operating systems work that we're doing here in the ParLab, or doing there in the ParLab. And so you might ask legitimately the question, what actual operating system support do we need for Multicore? And perhaps we could just take Windows or Linux or something and port it and just be done with it. And you know, these are mature operating systems. There's a lot of functionality in there. It becomes very hard to experiment with. It's possibly fragile. And it may or may not be what we actually want. So the approach that we're taking in the ParLab is to actually say, well, suppose we start from scratch. What might we do? Okay, and we can do this because we're not designing a product, right? We don't have to support everything right at the beginning. So clearly, applications of interest, and what are applications of interest? We're really kind of looking forward, asking ourselves, what are people going to want going forward with Multicore applications, possibly on the client? And clearly, the whole point of this is there's going to be explicitly parallel components are key, okay? Because if we take Multicore as you know, as a given for a moment, that means that we're hopefully doubling number of cores with some short time frame, and the only way we're really going to be using that is getting parallelism. So this is almost goes without saying, okay? So if the thing we come up with doesn't support parallel components, then we've got a problem. You know, obviously direct interaction with the internet cloud services, that's clearly important as well, okay? And so nothing that we do ought to prevent that. Interestingly enough, just that a remote interaction gives us some security and data vulnerability concerns, which perhaps we can address. And a lot of these new applications that seem to be of interest to people have real-time or responsiveness requirements to them. People are talking about new GUI interfaces, they're talking about gesture, they're talking about audio and video. And so we would want to see whether we could actually exploit Multicore to give us some better, better real-time behavior. And you know, related to that is responsiveness. Okay, so real-time I usually think of explicit deadlines or perhaps some streaming requirements of frame rates, whereas responsiveness has to do with, you know, I click that device and I better get something that happens right away. So I'm just going to flash this up here. This acronym was just an amusing one that I came up with, but it sort of reflects some of the things that were really of interest to us. And it's RAPIDS, and it stands for responsiveness, agility, power, efficiency, persistence, security, and correctness. As all acronyms go, this one's not perfect, but it kind of gives you a flavor for some of the things that we're interested in. And namely, you don't actually see high throughput as a key requirement. It's almost a given that, okay, sure, we want to do well computing, but these other things are equally important to us. And I'm not, we can debate acronyms some other time. But so what's the problem with current operating systems? Well, I don't know. So they often don't really give you a clean way of expressing the application requirements. Okay, and I put often in here because there are many there are counter examples, not many, but a few. But they might not let you say things like, what's the minimal frame rate I need, or what's the minimal amount of memory bandwidth, or QoS, or whatever. Perhaps they don't give you guarantees that the application can actually use. So, gee, I've made this component work really well in isolation, but the moment I put it in with a bunch of other things, then suddenly it doesn't work well anymore. Okay, and that's because it's being interfered with. And there aren't good ways often to express that a particular component cannot be interfered with in order to really have the behavior intended. Full custom scheduling is often not an option. Now, why would I say something about that? Well, if you think about future client applications and a lot of the work that Kurt just told you about, the parallelism there depends on a scheduler that's application specific. Okay, it's particularly tuned for the application. And if we're interested in parallel components in the future, then we really want to make sure that we can support whatever kind of scheduling is needed. And this one's almost funny to put often in question mark, but how are security or correctness actually part of modern operating systems? One might hope so, but not always clear. Okay, so the way I view the advent of many-core is it sort of exacerbates all these problems because there's a lot more resources that we could either use well or poorly. But it also provides an opportunity to sort of redesign things from the ground up. And so I'm going to view many-core as basically a possibility. It gives me the chance to rethink a few things. And what I want to do for the rest of what my talk's going to be here is basically tell you about the model of the operating system we're thinking about and some of the interesting implications of that model. Okay, and that's pretty much where we'll go. And toward the end, I'll tell you about some future directions that we're going with and talk about a prototype and so on. So first thing I want to tell you about is this idea of two-level scheduling and space-time partitioning. And it was kind of interesting when Burton Smith came out to give a talk recently. I was kind of nodding my head. Yeah, okay, yeah, I agree with that. So basically, two-level scheduling, as I am using the term, starts by saying, well, instead of the standard monolithic scheduler that you often see in an operating system, there is something in the middle whose job it is to try to do the best it can at satisfying everybody. Okay, and oftentimes you'll find something, it's got lots of options and tweaks and so on, but it's basically monolithic and there. And instead, what we're going to do is we're going to split it into two pieces. One is the resource allocation and distribution. Okay, and what the idea here is that there are entities in the system, and we're going to decide to give them resources. And we're not going to try to figure out how to schedule those resources. We're just going to say, okay, we're going to give you so many cores. We're going to give you so much memory bandwidth. We're going to give you so many resources. And the decision about that is going to be based on constraints about how fast we want that thing to run or our observations of the way it goes in the past. Okay? And that's going to be our high-level decision is I'm going to hand resources to you. And then at the second level, the application is going to use its application-specific scheduling to use those resources. Okay? So this is kind of a two-level approach here. Now, yes, go ahead.
Physical or logical resources?
Well, that's a good question. Are they physical or logical resources? Perhaps I will defer that question for a moment. I'd say that ultimately every resource has to be virtualized in some way, but they're going to be as physical as possible. Okay, because that's going to give us better guarantees of performance. Okay? And you can ask your question again in a moment. We'll see whether I answer it. Okay? Now, so this idea of spatial partitioning starts out as a very simple one. So here is a 64-core multi-core processor or chip. And basically what a spatial partition is it's a group of processors with a hardware boundary around it. And so up front, I'm admitting of the possibility of hardware support. And one of the nice things about the ParLab is we actually have the ability to experiment with new hardware wrappers around processors. And I'll show you how we can use some of that in a moment. But basically, it's a group of processors within a hardware boundary. And the boundaries are hard. So here's an example in which I've taken kind of the 64-core chip and I've divided it up into chunks. And the key idea here is basically to go after performance and security isolation by that's performance isolation and security isolation. Sorry, that should have put parentheses around this. By dividing up the resources. Okay? And so each partition here essentially receives, in principle, a vector of resources. So some number of processors, some dedicated set of resources which it has exclusive access to, for instance, complete access to hardware devices or dedicated raw storage on a disk or a chunk of the cache. Okay? And then some guaranteed fraction of other resources. And here's where hardware might help, things like a fraction of the memory bandwidth. Okay? So I'm assuming here that we might actually have the ability, and we do have preliminary mechanisms for this, to actually say, gee, this partition gets 30% of the memory bandwidth, and nobody can interfere with that 30%. Okay, now, if we don't actually have that hardware available, then we can try to emulate that. But anyway, fractional other services. Yeah, go ahead.
Is it programmable? Can the operating system say, now I want 30%, now I want 50%?
Oh, sure. So my assumption is that this hardware mechanism is fully under the control of the operating system. Yes. Okay, so yeah, 50%, 30%, 20%, whatever, some fraction. Yeah, go ahead in the back.
You thought about how this could interact with a hypervisor as far as allowing to punch through the OS process model down to the hypervisor?
So what we're going to do for the moment is let's get rid of the hypervisor. Okay, what I'm going to replace it with is something I'm going to loosely call a nanovisor. Okay, and I'm going to do that simply because calling it a hypervisor has baggage. All right, so now let's take a look at something about, so what the first thing I want to do is, okay, this seems interesting and maybe I can understand that performance isolation might be useful, but it seems like I burned something in performance right off the bat by clipping off, isolating things to one set of processors or another. It's interesting, we actually have some folks in the hardware group that have done some experiments with spatial partitioning, and what they found here is that, in fact, if they just sort of take two applications or multiple applications and run them simultaneously, just multiplexed in sort of a standard OS fashion, that actually doesn't work as well as cutting the machine down and giving sort of part of the machine to one app and part of the machine to the other app. Now, what's interesting about that, though, is you can't just divide it in half. That's this green bar. The sort of, that's not the best. The best partitioning is something specific to the apps. Okay, maybe I give 4 processors to one and 60 to the other. Okay, so there is some spatial partitioning that is best for those two apps other than just running a regular scheduler. And this is kind of an interesting possibility here from performance standpoint. Now, I'm interested in spatial partitioning for lots of other reasons, but I just wanted to show you this to indicate that maybe it doesn't cause you to throw out performance right away. Question in the back, yeah.
The explanation for why that's the case?
Basically, one way to look at this is that applications don't linearly scale in many cases, and so there's a point beyond which, as you add more processors, the bang you're getting for your buck is not being made up for by what you're losing at the other application that could be given those processors. So this is kind of an effect of not perfect linear scaling, among other things.
Can you identify the patterns that produce those kinds of applications?
You mean the patterns in the sense of what? Yes. So these, I don't think these were particularly done with patterns. These are actually just a set of standards, parallel benchmarks that we.
No, but the patterns in terms of the behavior that shows that.
I cannot. I apologize. I don't have an answer for that. That would be that's a very interesting question, which I am now going to try to figure that out. That's a good question. Okay. So obviously, if we just stuck to spatial partitions that were fixed, then that's not going to be useful, right? I mean, we obviously can't fix something at boot time and keep it that way. So clearly, there's going to be what we like to call space-time partitioning. And here's an example of a 16-core machine where we've partitioned it up, and the colors represent partitions. And you can imagine that over time, things vary a little, right? Okay, this is probably not at all surprising to anybody that we might want something like this. And why is this not just standard scheduling? Well, what's interesting here is that, first of all, these time slices are somewhat coarser granularity than maybe a normal OS time slice. So we're not trying to go after the really fine-grained multiplexing. That would be for the second-level scheduler. What we're trying to do is we're trying to put these isolated machines out there that, that basically are not disturbed by other applications and use their second-level schedulers to get their performance. Okay? So I would actually like to call this controlled multiplexing, not uncontrolled virtualization. Okay? Or another way to look at this is, for instance, we're planning on scheduling these slices a bit in the future because we know enough about what we're trying to give in terms of resources. Okay? And also I'll point out that resources are gang scheduled. So this is important for a lot of different parallel programming paradigms that when I give a set of processors, I'm going to give them all at once. And I'm going to give all the resources at once. Okay, and I'm going to take them away all at once. And the reason for that is that that gives the user-level scheduler the ability to do a better job of scheduling its resources because it knows what it's got when it got them. Yes?
Are actual measurements of what it costs to reconfigure your partitioning?
So we don't have a lot of numbers of that form right now because, first of all, our prototype's in the early stages. And the second is we're actually playing with hardware support. So I would claim that as a hardware person, I could make the changing of this as cheap as possible for the software, but it's not clear that's a good trade-off. So I think I could tweak the knob in lots of ways as to how expensive this is. Why don't you ask me that question again in a year or something, and I might have a better idea as we really push these ideas. But you can imagine that if the only thing we're talking about is processors, it's the cost of a context switch. If what we're talking about is setting up registers in the machine to get bandwidth isolation and so on, it could either be more or less expensive depending on what kind of support we want to put in. Okay, now I would claim it's not going to be that expensive. We shall see. So let's push this idea a little bit further. So if I'm space-time partitioning things, then that isn't really something a programmer wants to deal with. So obviously we need a little virtualization, and this is getting back to your question earlier. In our view here is an abstraction we call a cell, which is basically a user-level software component with guaranteed resources. Is it a process? Is it a virtual private machine? You know, we got into a lot of arguments once about whether we should call this a process, and in fact, I was resisting because it's more, it's less, I don't know. But there's an analogy with a process here. It's got code, it's got an address space, it's a protected domain, but maybe there might be more than one protected domain, or there might be no paging, so it might be more or less than a process. Okay? What are the properties of a cell? It has full control over the resources it owns. So I would say that while the cell is mapped to the hardware, it can use any resources we give it access to. Contains at least one address space. It has a set of communication channels with other cells, and I'll show you about those in a moment. And then it has a few other things like a security context, which maybe automatically encrypts and decrypts information as it crosses cell boundaries. These are a few things we're playing with. And maybe has the ability to manipulate its address mappings via some sort of paravirtualized interface. So this is a potentially pretty low-level machine that we're handing to a piece of parallel code, a component, so that it can make best use of it. And realize that the reason we're proposing something like this is to stay out of the way of folks like Kurt, who are busy trying to tune things to run as well as possible. We want to make sure that we provide a nice, clean environment. Yes?
Would something like a network device map onto these cells?
So a network device would typically, I'll show you a kind of a funny sketch in a moment, but a network device would typically get a cell, or maybe a couple of devices, depending on how you want to program it, might be put into the same cell. So we might have the network devices get a cell with a set of resources, and they're allowed to use them any way they want. Okay? And so when mapped to the hardware, the cell gets gang-scheduled hardware threads. We call these hearts, the guaranteed fractions of resources, and so on. Okay, question? Yes?
How does this deal with... So the essential software, I'm presuming, is multiple resources of each given type.
Right.
What if there's just one instance of a given resource type? How is it dealt with?
So if there's one instance of a given type, there are a couple of possibilities here. One, you give it to exactly one cell, and that cell forms the multiplexing. So you actually have some software that acts as a gateway to that device. That would be more in keeping with this philosophy than trying to multiplex it, that one device automatically underneath, because that would turn us from a nanovisor into getting into the hypervisor view. So it's more that you'd have a software component that would do explicit multiplexing of that. So what do we do with cells? Well, here you might see an application divided into an explicitly parallel core piece and some parallel library with a secure channel between them. So it's kind of a component-based model. Applications are interacting components. And, you know, we get composability here. Obviously, we can build this parallel library component separately from this application. This might have some properties that we tune, and then when we use it in this application, we keep those properties. So the other interesting thing is that cells being co-resident on a bigger chip, so remember we're thinking about many core, means that potentially you can cross this protection domain rapidly just by sending a message. Okay, there's no context switch involved, which is kind of what we were stuck with a single processor or a small number of processors. Okay, so this is kind of echoes a microkernel view in some sense, but is different in that A, we're giving it to applications as well as services, and B, we have this potential of very fast crossing of domains. And within the cell, you have fast parallel computation. So we're keeping parallelism fundamentally here. And of course, you know, here we could see what might be the full application, where there's some real-time cells that are doing audio and video. The file service is part of the OS. Device drivers might be running in their own cells, and so on. Okay? Now, of course, it's all about the communication. So I've been kind of ignoring that a little bit, but we're interested in communication for lots of reasons. Communication crosses the resource and security boundaries. The efficiency of communication impacts how much decomposition you're willing to do. Here's an interesting issue here. So we're interested in quality of service. And one of the things we're interested in is the potential to give a fraction of a shared file service to applications A and B and guarantee that. So what does that mean? Well, that means that potentially I have to restrict the amount of number of requests per unit time across these channels to make sure that I don't oversubscribe that service. So we're definitely interested in being able to guarantee to some application that needs it a well-defined piece of something. You know, another question which is interesting is, so you send a message, but this cell happens to not be mapped at a given time. Does it wake up right away? Okay, that would be sort of the traditional event-driven approach, and it's certainly something we support. But something more interesting that we support is that, no, it actually wakes up when the thing is scheduled in its time slice. Okay, and so interrupts and events are not the only way to send something. And as a result, you don't necessarily have to disturb a parallel item that's running well. Clearly, we would support interrupts because those are occasionally needed, but we're actually kind of the view that they're needed a lot less than people use. And then, of course, the communication defines the security model. So there's a couple of those we're looking at, but it's really about who do you allow to communicate with whom. Okay. So you could say here is, I don't know, tessellation, right? So we've got a couple of large compute-bound application, a real-time app. We have some file storage going on. Maybe we have a networking component that's doing intrusion detection continuously. Maybe we have something doing GUI and interfacing with the user in other ways. We might have some device drivers and so on. You know, you could see how this scales. I mean, how this might go, right? Here's another view for more of a so this was kind of a client version. Here might be a server version where we have a bunch of chips, and we actually put QoS guarantees on, say, access to memory bandwidth, access to inter-chip communication, maybe access to the disk, and so on. Question? Yes?
What do you think happens when one or more new applications come into the workload?
So what happens when one or more new applications come into the workload is you have to change the allocations. And I'm going to talk about that in the remaining part of my talk. Okay, so clearly static situations are great in the short term, but they're not so good in the long term. Okay, so in fact, let's talk about resources here for a moment. Good question. So another look at two-level scheduling. So why do we want to do it? So the first level is really about globally partitioning resources to meet the goals of the system. Now, what are the goals of the system? Okay, they're defined by policies that are both global and possibly local. And so there's, you know, you could imagine an arbitrary complexity here. But it's busy partitioning up the resources of the system to various cells to try to meet some goals. And of course, we want to make sure that the partitioning is constant for some sufficiently long period of time that the local schedulers can do a good job. Okay. Second level is application-specific scheduling, okay? Goals might be performance, real-time behavior, responsiveness, and so on, and this is sort of running within the cell. There's another scheduler that's running at user level and doing whatever it wants with resources to meet the goals. Okay, let's see. I think this is all I want to say. All right. You know, second level schedule can defer interrupts and so on locally because it's got full control. All right. Yes, sorry.
So one of the problems with the constant for sufficient time, sufficient time gets very big, is in consumer client-oriented applications in parallel, which we're all monolith apparently, so in lots of chips. Things change on the order of milliseconds and mouse clicks.
Sure.
Right?
So if the user, so the way I would view that is if a user actually makes a mouse click and wants some major change to happen, we'll be perfectly happy to stop something that was running well to handle the user. I mean, that's this idea of trying to keep things constant for long enough time to do well is only true if that's not the thing the user really wanted. So this is potentially a trade-off between responding rapidly, that's responsiveness, and performing well, and we will go for the responsiveness case in the case of the user.
So the question fundamentally is, with this kind of architecture, can we respond quickly enough to give users a good experience?
So we think the answer is yes. We don't know for sure yet. Basically, a couple of ways of doing that. One is keeping excess resources that you know how you can get a hold of when you need them. And so you basically are giving the excess resources to be used, but you can grab them right away when you need to do something like that.
One other question is that you look a lot at partitioning of memory, and you haven't talked a lot about virtual memory and the impact of virtual memory on these plans. Can you say more about that?
So virtual memory in the sense of seeing a memory space that's bigger than the amount of DRAM you have. I mean, there's a lot of different ways of using virtual memory. Okay. Why don't we, yeah, let's take that offline. But, you know, basically you can imagine partitioning the physical memory and then giving it access to do anything it wants with its virtual memory, including paging in an application-specific way. So just briefly, I want to make sure that my last colleague has a chance to talk. Oh, question, yes.
About memory coherence,
yep.
Are you going to assume that within a cell, all processors have a coherent memory?
So I think that we probably want to assume that a cell has shared memory, cache-coherent shared memory within it. But we are certainly looking at architectures for which that wouldn't be true. So, you know, our view is kind of you use whatever resources you've got in a cell, and if you don't have shared memory, you use message passing or something. But that's a parallel app that's running in a container. Now, you may ask, how can I build a container that, or an application that can be handled both with shared memory and message passing, and it picks one. I'm going to avoid that question for now. That's a potentially hard question. Yeah?
One question. For the first level global partitioning resources, how is that determined? Is it that the app specifies its quality of service in abstract semantics and those are translated to system resources? Or is it more specific, where it specifically says how much resources it wants?
It's either. So that's a great question. Does the app give something abstractly in terms of a frame rate, or does it say it wants so many processors? We're actually supporting both. There's what I would call an impedance mismatch between what the programmer understands, which is, say, frame rate, and the resources. Okay, and I think that a lot of systems don't even try to address that, and we're experimenting with ways of figuring some of that out automatically. But there is that impedance mismatch, but we actually think that rather than accepting it as being a problem, we want to actually address it. So basically, what is the state of the system is specified in what we call a space-time resource graph. This is just a chunk of it, but basically cells have what we call space-time resources, which might be 4 processors for 50% of the time, et cetera. And then potentially they can be grouped, so you can actually put resources up higher here, which really means that resources can be allowed to move from cell to cell within the group. Okay? And the guarantees are made at the cell level here. So how do we build this thing? So we actually have a partition policy service or layer. I actually see an inconsistency, I apologize, that is busy doing the allocation, and I'll show you the structure of that. It produces space-time resource graphs, which then get implemented underneath by a mapping layer that takes the graph and decides how to map that to the hardware, and into a set of slices, and an underlying partition layer that basically is the nanovisor that provides the hard boundaries underneath. Okay. And you could almost say that this mapping layer makes no actual decisions. It's constrained by what it's been told to do. It's really doing a form of bin packing on this, but it's a form of bin packing that's already been verified to be workable before it's been handed a graph. Yes?
Even if we do maintain coherence, we're obviously not going to maintain NUMA, or going to be NUMA. How does that impact the scheduling?
Well, so you would, my view has been, for many reasons, not just the NUMA issue, but other hardware reasons, that cells are going to consist of co-located processors, not one that's on one side of the machine and one that's on the other. So for any given machine, as your cell gets bigger, there will be some well-defined NUMA properties to it. But they won't be, the thing split in half and it's on opposite sides of the machine, right? My suspicion is that the cells will always be co-located to whatever extent is possible.
I guess the point is that the NUMA domains form sort of very strong boundaries, meaning that you really can't put data in multiple NUMA nodes unless the pattern in the actual application supports that.
Sure.
So you're trying to do this interesting mapping problem that's a lot harder because a NUMA is just uniform.
Right. So, okay. So now I understand your question. Let me give you here's how I would answer that question. I would say that if you've got a machine of some size and you want to chop it into pieces, the question is, can you build apps that run well? Okay. Now, the flip answer is it's not my problem. The non-flip answer is the following. We're actually looking at interfaces to provide topology information to a layer that's scheduling and deciding how to do that. You could say that if your app can't handle NUMA very well, then it needs maybe to be rewritten, or you need new patterns to look at. The OS is providing the services basically of this machine boundary that's kind of a clean boundary, and being able to program a NUMA machine well is actually, I would consider, part of the higher layer than the operating system. So that's maybe an interesting debate that we could have tomorrow, which I encourage. Okay, so I should finish up here, but let me just show you here. In fact, I'm not going to walk through everything, but here's an example of our actual architecture. I wanted to show you some layers. So we've got the partitionable resources down here. We've got the mechanism layer, or the nanovisor, is busy implementing the partition, implementing channels, maybe doing QoS enforcement. The partition mapping and multiplexing layer is basically still part of the trusted code base that takes space-time resource graphs in and implements them. So there's a validator to make sure that you don't try to do something that violates your security in some way, like shutting off a key operating system cell. And then it plans the resources, and then somebody multiplexes it. And notice that there's kind of two key ideas here. Admission control. So we actually reserve the right to reject requests. Please start this cell. No. Okay, now, that always throws people for a loop, right? But if you don't reject requests, there's no way to make guarantees. Okay, I'm going to say that way. What do you do when a request is rejected? Well, that's interesting. Maybe you ask the user to change their preferences or something, or maybe there's an automatic mechanism. Now, what I've shown here, let me just talk about this adaptive loop, is in principle to meet this impedance mismatch that I talked about earlier. We're expressing frame rates, but we've got cores. What happens is we're measuring performance, we're building potentially models of how that performance is going, we're adapting resources, changing our graphs. You can see the loop here. And in principle, admission control, when it can't make a simple change, might ask for a major change, and as long as it meets the policies, maybe that major change will be admitted. Okay, now ask me the explicit details about this. I'll tell you we're still working on it for obvious reasons, but this is the philosophy. Okay? We actually have several different modeling things that we're looking at for building this, and we'll talk about this tomorrow. But you can imagine, I know Burton Smith really likes this notion of a convex optimization problem, where once you've got a definition for how things behave, then you're trying to optimize for something. Yeah, question?
Does it imply the previous slide that you might reconfigure the system where a longer running application might see its resources change, like You know, I mean, maybe I was given 16 cores to work with, and then suddenly I have like 4 or something like that.
Yeah, so there's explicit interfaces for resource changes. And so if you say that I can deal with resource changes and be a good citizen, then you'll be told about that. Okay, I'm getting the, let's get ready to finish up here. But yeah, so there's an interface for that. Scheduling inside a cell is just user-level scheduling. There's lots of interesting things there. There's also questions of how to divide applications into cells. You can see the obvious questions. If the granularity of the cells is too small, then the policy layer's got too much complexity and can't really do a good job. And so that's interesting. And then finally, you could imagine things we might want from the hardware. So like, for instance, obviously you want it to compute well in parallel, but partitioning support, QoS enforcement mechanisms, fast messaging support, these are all things we've been looking at. And by the way, Dave mentioned RAMP earlier, is this great emulator that allows us to add these mechanisms in and take a look. And so, for instance, we've actually got an emulation of a memory bandwidth partitioner mechanism that we've looked at, and you can show that we can get good performance isolation having that mechanism, and it's not too expensive. Okay, so I will conclude. I'll be around for a couple of days, so plenty of questions, I'm sure. But I talked about space-time partitioning and cells is basically a new mechanism on which to construct things. This partitioning service is kind of an interesting heart of this process, and we're actually building an OS right now that's got several of the nanovisor pieces to it and runs code. We had a demo and is probably about to go through restructuring number 5,496, but you know, we're working on it. So, all right, I'll stop now. Sorry. Okay. Sorry.
Let me make a modification here. And we need to make sure that your resolution is at 1024 by 768.
Okay, I'm Bodik. I'll talk about the web browser part of the project, which is really how the software stack would look like on top of the operating system that you just saw for the case when we are talking about client computation. So it is true that it was the browsers what made smartphones popular, because mostly people started buying them after the browser became usable on them. But in a sense that in the same vein they failed. They serve as successful browsers on those platforms, but they are not what they have become on laptops, on desktops. On those bigger platforms, they become the de facto application platform of choice, and many, if not most, new applications are developed in the browser. This is not the case on the mobile phone, and that's partly because of the performance. If you look at New York Times front page, it may take 15 seconds to load on your iPhone. And the reason is not that the network is slow. This was done actually on a fast network. The reason is that your browser is essentially a LaTeX kind of compiler running on your phone, and it's very computationally intensive. And so the reason is that there is a lot of abstraction tax that you pay when you use the browser. That's the tax you pay for productivity, the fact that you have a really powerful layout engine, an extensible scripting language with dynamic types, which you can embed DSLs very easily into. And that all shows up. And we did an experiment with a simple application written on top of Google Maps API, rewrote the same thing in C, and it was 100 times faster. It was probably 100 times harder to write also, and we'll get back to it in the talk. But that's the reason why people don't use browsers to write applications. Mostly they use things like Android, Silverlight, and iPhone SDKs and their siblings, which are a little bit more flexible, powerful, but they are lower level and more efficient. So the browser is CPU bound, and what's inside? There is essentially a parser that takes whatever the input is, HTML, CSS, gives you the DOM, which is the abstract syntax tree for the document. And there is a selector engine which takes the CSS styling rules, effectively, and maps them onto the DOM. I'll talk about it some more. Then there is the layout engine, which positions those elements on the screen. And then you render, which is you just move the bits, blend them onto the graphics on the screen. And then there is JavaScript, which provides the application logic reactivity, and that may actually redo everything. And which of them is expensive? Turns out that all of them are expensive. So speaking of Amdahl's law, you cannot really sidestep any of them, and all of them need to be optimized. And so we look in the project at the top 4 levels. We have a story about the language, which is perhaps the most important story, but it's not based on JavaScript, and I'll try to justify why later in the talk. So these are the 3 main driving forces, I'd say. We care about low-power devices, phones, and in fact smaller, predicting that phones are the next coming computing platform that we'll use, but it's not the last one. The next thing will, as computers move from the stuff that you have under your desk to your lab to your hand, they'll end up on your ear somewhere, and not so far away. We look at client applications. They'll be interactive. They'll have sensors. They'll have augmented reality, which take all the sensors together and help you live your life. And we look at the future of productivity languages. I think one reason why JavaScript became popular was that we had a lot of spare power in the 90s, and we didn't have the application demands. There was sort of more surplus of compute power in the 90s, and scripting became popular. Now you see the opposite pressure. People want to write applications with scripting languages, but the compute power is gone, or the improvements are gone. So what the future of scripting languages looks like is a major question here. So this was the original motivation for the browser project. We realized it's not only a phone. Once we observed that one could put a little laser projector into the phone and turn it into a tablet computer in a bar. And that was just a vision. This is a mock-up picture we did by actually holding a real projector above the desk. But turns out that Microvision released this laser projector just about a month ago. You can buy it for $550. And I don't own it yet, but apparently it's very impressive. You cannot fit it into the phone yet because the projector itself is about as big as the iPhone, but the projector itself is like the tip of this pen. So I think this will actually, you will see it soon. Please.
The driving force is low power. Does that include battery life for driving?
That mostly includes battery life, yes. But of course, there is heat dissipation connected with it, but I think battery is a good proxy. So here is the stack of the parser. So the parallel lexer and parser here, of course, as before. There is the CSS matcher, which I'll talk about, the parallel layout engine, and rendering, where we don't have many results yet because you really need to rewrite OpenGL to be parallel, but at least we're investigating how parallelism could help over there. Now, the whole thing is not written from scratch, although currently mostly is. It will be generated in the spirit of parser generator. That you'll have a generator of parsers, and you'll be able to create multiple variants and auto-tune across the space of the generated things. The same for the layout. We have formally written the specification of most of the CSS with attribute grammars with the goal of actually generating that engine automatically with various optimizations that will be of serial nature, such as incrementalization, and parallel nature, such as task parallelism.
CSS fits in an attribute grammar?
It seems that it does,
wow.
Yes.
Which attribute grammar formalism did you guys choose? Or we can go into that.
Okay. What are the key differences among them that you have in mind?
I don't know. I thought there were, it's like parsing. There's different varieties, aren't there?
Okay, I guess we'll have to take it offline.
Okay.
But it doesn't end here. So our scripting story is a constraint-based language that combines constraints with events. So it really gives you the ability to put together the layout of the page, the semantics of the layout, and essentially reactivity. And there will be a synthesizer whose output is going to be an attribute grammar. And then again, you can go through this engine that generates parallel and incremental evaluation. So let's start with parallel lexing and parsing. So lexing is a simple task. You have essentially a string of characters here, and you need to break it into tokens. And the tokens are described here with the regular expression, which really corresponds to an automaton. So you need to run this input through this automaton and determine at each step which state of the automaton you are. It's as simple as that. The problem is that, of course, this process is naturally serial. It's embarrassingly serial, you could say. You cannot make the next step before you know the state of the previous step. And yet the way we would like to parallelize it is to actually break the input this way so that you do not need to obtain multiple files in order to obtain parallelism, that you can actually parallelize one file, one stream. Right? So for stream processing, this seems to make sense. So here is the observation. In at least lexical analysis, maybe less so in regular expressions pattern matching, if you start your lexical analysis in any state, after some time you end up in the same state. So we pick an arbitrary state, not necessarily a correct one, but after 3 steps in this case, depending, because there is one token here, we all end up in the same state. So there is sort of a notion of small warm-up prefix that is sufficient to get you pretty much, no matter what state you are in, into a correct state, even without having seen what was before in the input. And this observation lends itself to this algorithm that you take your input and split it into chunks with certain k-character overlap. And what you do there, well, you just predict that you are in some state. It is this. And you run each of these parallel processes independently, starting from this good state that leads to usually a good warm-up. And you realize that, yes, indeed, we guessed the state correctly after the warm-up. Even though we started from a wrong state, the state was again correct. And so we check for the matches in speculation. It's a speculative algorithm, and you get pretty nice speedup because in this domain, things seem to be predictable. So here is the speedup on the IBM cell processor. For large files, the speedup is nearly perfect. For smaller files, which is about 250 kilobytes, scalability is not that great yet. We need to work with the OS and our hardware to tune it a little bit better, but it's still not bad. On 5 cores, you are still nearly 5 times faster than Flex, which is the well-tuned serial lexical analyzer. Parsing. Parsing is the step that comes after. You obtain a string of tokens, not characters. So this is the result of lexical analysis. And your program is described with a context-free grammar, which might say that the program is, in this case, just one function with one argument variable, list of statements. A statement can be an assignment of expression to the ID, an if statement, and an expression is ID plus E, and so on. We took a compiler class, you know what I'm talking about. And what a parser does, it goes through input usually left to right and identifies things like, oh, I have an expression here, here, and here. And I also have an expression here. X greater than y is also an expression. I have a statement here, and therefore I have a statement here, and therefore the whole thing is a program. And this all appends left to right. So the context that you see on the left is important. Now, if you want to do it in parallel, you give one processor only the left part of the input so that another one can work here. And the way we do it is that there will be a sort of main parser going through the whole input, the one that does non-speculative work. And on those chunks that are ahead, there will be a speculative parser that will try to pre-parse the input and essentially allowing memoization for the main parser. We will just skip over when it gets to that part. So that pre-parser will have to guess at the context of the main parser, which of course it doesn't have because it's still working on the left. So it will guess correctly that, well, these are expressions and that this is an expression as well. And now it will have a little bit of a conundrum because it will come here and say, well, this looks like an expression to me, and indeed it is, because you can derive that from E. It is an expression. Of course, in this context, it is not. These parentheses are not part of the expression parentheses. They are part of the if statement parentheses. But nothing went wrong. You just memoized here that this is an expression, and when the main parser comes to it, this if is not going to look for an expression, so this work is, very redundant, a little bit extra work we've done, and it will come here, it will skip over this because we have already parsed it as expression, and it will also, by the way, skip over that part because that has been already pre-parsed as a statement. And now it can put these two pieces together, realize the whole thing is a statement, across these boundaries, the whole thing is a program. So it is a speculation that, based on the context that you glean from looking at the tokens in the input, you try to predict the state of the parser and see whether this is indeed E. And sometimes you do more work, but you never go wrong. And here is some fresh data on predictability. So here are various pairs of identifiers that you can see in the input. And what you see here is that if for each pair you make 2 guesses as to the state of the parser, you are doing pretty well. This one, you get about 50% probability that you guess the state correctly. And the data actually are better than what you see here. All these bad-looking data, with a little bit of static analysis of the grammar, which we haven't done, would probably go like this as well. I'd rather not go into it right now. So this is the parser. Now let's go quickly to the CSS selector matcher. What happens in this step? You have your document, which has a root, and then it has a paragraph, and another one. Here has a text and an image, and here is another paragraph with a bunch of words in it. This one is bold. And the goal is to take these styling rules, such as this one, which says image that is part of a paragraph needs to have the following font size, and you have a bunch of them. This is the essentially rule, and this is the styling prescription. You need to, for each node, find the corresponding rules. So in this case, these are these 2. And you have about 1,000 nodes and 1,000 rules in a typical document. So there is quite a bit of work. In fact, this seems to be the most expensive component in browsers. And well-tuned websites like Gmail don't even use this functionality because it's so slow. And in a sense, you could say they sacrifice software engineering goodness because this matching is very slow. So let's see what we did. Because this is huge data parallel computation, the parallelism is obvious. You just need to know how to slice it. And the most significant things actually didn't come from parallelism, but from locality optimization, such as tiling, making sure that you have in the cache only the important data at the time, and then you go through the next one and next one. So these rules are split in intelligent ways so that only a subset of these rules is in memory at a time. And if you look at the speed up, we started with an implementation that is similar to what we have in the WebKit driver, WebKit browser. And after L2 optimizations, it goes probably to factor of 3. After some L1 optimization, it goes to factor of about 25. And then you add to it speed up from parallelism, which is about a factor of 3 for 4 cores. We are quite flat after that, but hopefully more work will help you there. But together, you are about 60x faster than the original, which probably makes this a non-bottleneck in the browser. So let's talk about CSS. Rather than telling you right up front what happens in this parallel layout engine, let me tell you why formalizing CSS may make sense. So here's a piece of CSS, a few nested boxes with floats. And here are how they render on 3 major browsers. And on each of them, they are different. And we still don't quite understand exactly where there is ambiguity in this part of the specification. Actually, Leo probably understands it. But I'll show you a simpler story which tells you why having a formally specified spec may help you find holes before you actually release the spec. So here is 3 nested boxes. You give the width of the inner one. This one needs to be half the width of the parent, and this one needs to be as small as the child. And you probably immediately see the problem that you have a dependence that this one depends on this, and this one depends on that. So you have a cyclic dependence. Of course, you can solve this layout problem, and perhaps with fixed point iteration, but you know what the output looks like, right? It will be a box that these 2 outer boxes have 0 width, because that's the only condition under which you can meet both of these constraints. And so this is essentially what spec silently says, that this is what these rules mean. When an engineer had implemented those constraints, a browser engineer looked at it, probably said, well, either I don't like the cyclic dependencies because I want to have a bounded number of passes through the tree, or he didn't like the output for the specification. So, well, he said, well, I need to break some of these constraints because I cannot satisfy all of them and still get something good looking and good performance. So he either breaks the outer constraint, so now this outer box is not shrink to fit to its child, or he breaks the inner box, and now this one is not half of its parent. So which one would you pick if you had to break one constraint? Of course, both of them look equally good, but they decided for this one. Well, not all of them, all 3, probably one of them decided, and then the other just copied the semantics because this is how you interpret the CSS spec when you implement the browser. You see what the other browsers do, and then you do the same. So no wonder that these ad hoc decisions as to which constraints are broken, and just the fact that you implicitly drop these constraints leads to surprises in CSS. In this case, at least they made a decision that this box doesn't stick out, as it does here. But as this mug by the fan of CSS demonstrates, no, you are not always, so lucky. So here is why having a spec would help, because if you write it as an attribute grammar, you would immediately see, without seeing any particular document, but through static analysis, that you have the cyclic dependence and something is wrong and you need to resolve it. And rather than leaving it to ad hoc dropping of constraints, which is, of course, surprising. So having these benefits, and Leo did find some surprising holes in the spec, especially when it comes to tables. You can also then write a parallel layout engine. You can look at how layout is computed and identify parallelism in it. And so here is how layout happens. Again, you have a tree, which is pictured here. You have one paragraph, and here you have another one. But there is this image here, which is a float, meaning the text needs to flow around it. And so what do you have? You have a body, you have two paragraphs, you have the word hello. This guy here is a float, which means it can flow to the next paragraph, and the text goes around it, and here is this rest of the paragraph. And the CSS layout, as is LaTeX layout, is so-called a flow layout. You lay things one after another, essentially the way you lay bricks. Often the specification says where you need to put the next thing after the previous one has been laid out, and you know what part of the screen is free. Especially the case in LaTeX, the description does look like that. And so the layout really looks like, okay, what is the layout? We need to compute the sizes of each element and their coordinates, x and y. So you start by saying this is the width of the whole thing, this is the font size, and these last two x and y sort of where the cursor currently is. And then you go in order through the graph, computing things. This is the way you would do if you lay bricks, one after another. And of course, there isn't much parallelism here because there are these dependencies. After all, the position of this paragraph depends on this paragraph, and in particular, where these words can go depends on how much space this picture takes up. But if you look at the attribute grammar, fine-grained dependencies show up. And now the thing is all of a sudden more parallel. You can now see that, I can compute font sizes of this without touching this part of the subtree. And 5 phases all of a sudden appear. And in the first phase, you compute font size and a temporary width. Then you go bottom up. Both of these phases are parallel, sequentially after another, but parallel themselves. And then you do another phase, and you go up. And in the fifth phase, you are ready to compute the absolute positions. And here are some preliminary speed-ups. This is from a not quite a faithful implementation yet, but on 4 cores, about 3. This is going to hopefully be more complete soon. So what you get is that when you have formal spec, you can then automatically, with an attribute grammar engine, actually find that parallelism and generate the engine with other optimizations, auto-tune over variants. What smarts will have to go here, we don't quite understand yet. Some part of the parallelism was discovered by Leo tweaking the grammar by hand, so those will need to be generalized into automatic parallelizations. So let's now look at the motivation for this language. So why constraints? So I'll try to give you, I think I have 2 or 3 reasons for why the scripting should be based on constraints. The first one is, the first one actually motivates why the language should have constraints and events together. Why it should have layout and scripting, in other words, in the same box. So here you see how you typically program in today's browser. If you have a tile, which may be a piece of a map, an image in the browser, if you want to position it somewhere or set its height, you will, in JavaScript, write something like tile.height. You take an x, which is an integer variable, and you append px, a substring to it. And this is then passed to the browser proper, and which will discover how high the tile should be, and it will lay it out. Now, what happens actually in the execution is that you take 15, an integer value, convert it into a string, concatenate it with px. Then you pass this 15px string down to the browser across the JavaScript C++ boundary. And there you, of course, dutifully parse it, break it into 15 and a flag. And now you know this was 15. So this is one of the reasons why browsers are slow, that not only the context switch from here to here is expensive, and therefore some research groups, such as the one C3 here and Adobe, put the layout essentially into the same language so that you don't have to cross this boundary. Still, this problem of optimizing this away remains, because it's not something you can partially evaluate, at least not with the standard techniques. So this is motivation for having one language where the layout part and the scripting part is together and can be optimized, and there is no expensive context switch. I told you about the application we wrote to understand how much abstraction text there is in browser, the one that was about 100x faster. It was quite hard to write. One key difficulty was that you had to write macros or whatever for converting between 4 coordinate systems, because you had a notion of coordinate out there, sort of longitude, latitude. Then there were coordinates of pixels. Then there were tiles within the map, because the map was built out of tiles. And there was one more which I forget. But I don't understand the code that Chris wrote, because this was not easy to get right. It would be much nicer if these conversions were not written in a functional style directionally. We didn't say how to convert, only what the relationships hold between these coordinate systems. So I would much rather write something like that. I would like to say there exists a relation from some family of linear relations between, and what is the relation? It's between the coordinates on the map and coordinates on the screen. And I'd like to say, well, if this x on the map is in this relation with the screen, then x plus 1 kilometer must be screen.x plus 100 pixels. And hopefully I establish sufficiently what that the relationship is. And from this description, a synthesizer will first come up what is this relation exactly, so that it is unambiguous, and then synthesizes a function. So that's where we are going with this. Motivation number 3 is that if you look at some web pages in terms of visual design, human perception, some of them are easier to navigate than others. This one is reasonably busy in terms of text, yet it is easy to navigate. So why is it so? The reason is that it is like this document, which I would call beautiful. It's an example of great design where you can navigate your eyes and really know where you are going and where the captions are for particular images. And the theory is that this is because it is an instance of a grid design. You first prepare a grid for your document, and then you put images, text into it. And so clearly, you have the images here. A bigger image covers not some arbitrary fraction of the page, as would happen in a typical web page, but covers these 4. And then the text comes here. And there is whole theory and informal guidelines specified for how to do it, but no language that would make it easy for you to follow this design, or better, that would make it difficult not to follow that design. In fact, we would like to give designers a way to easily build documents and make it hard to build others. So really, I think the long-term goal is to give designers a language for building such layout systems, such as CSS and these. Finally, it's events. So JavaScript events are sort of go-tos. If you have a box on the screen that you want to move, you write a piece of text which has 2 nested handlers, one and another one. And these are sort of first-class functions that essentially are your interrupt handlers. It's not quite easy to see what is going on. It's easier to see when you write it as a data flow program, where you say, I have a source. It's a mouse that each time you move the mouse generates a pair of coordinates that go here. You delay each by 500 milliseconds. And then they set the coordinates of a box on the screen. And now you at least see what that program was doing. It's easier to analyze because you know what is the flow of control. And because it's the same as the flow of data here. Data flow is an improvement. Then you start seeing it in scripting languages in terms of data binding and such, where you can refer to variables from your HTML document. It's not great when you have a more complex document, because it happens that you need to send messages this way and also that way, and these cycles may lead to oscillations and programs that have bugs. So what do we offer? We offer a system that does not have directional flow as data flow, but that is bidirectional or relational, where there is no particular flow. So let me just show you 2 fragments from a case study, sort of our driving application. So imagine you have a video player with the usual play button and the name of the movie. And this is important here. This is your timeline that you can grab and scroll, right? You can grab it here and scroll it. Here is an annotation window. So with this movie comes a set of captions. Each of them has a start time and end time, and they are displayed here in a scroll box. And as the movie goes on, the annotations march along. But you can, when you grab this and move it, both the movie needs to be rewound and these annotations. When you scroll these annotations and you click on, say, this one, the time needs to advance to this annotation. The movie needs to go there, and the annotation needs to be centered over there in the window. So that roughly corresponds, we believe, to what the interactive applications will be in the future. So here is how you envision we'll write it. What do we have? We have boxes with ports, but these lines here are just constraints. At this level, all these constraints are equality constraints. So this variable here and this variable here must always be equal. And in particular, look at the time. There is a video player which has a time port, and annotation display has a time port, and the slider, which shows you the time, has a time port. And all we are saying that these three are tied together. And any of them can initiate change in time, and the others need to adapt. But I'm not saying specifically in which direction the messages flow. That will come out automatically with the compiler. Similarly, you have a toggle button which tells you whether you are playing or not playing. And both this part and that part can initiate the change. I can press on the button and start playing. When the movie finishes, on the other hand, the activity goes this way because you want to gray out that button since the movie stopped playing. Yet I do not need to worry about these messages in both directions. I just set this constraint. So this is how, hopefully, these applications will be just glued together, even without messages. Now, I want to tell you how events would be handled here, and I have 1 minute, and I think I'll manage, is that what you see here is this annotation display, which showed all the annotations. You actually create them here. You get a list of annotations, and you create a bunch of boxes, just like in HTML. Think of them as boxes. And they are all put into the VBox. So you can think of the VBox as the parent in the DOM of these boxes. And you put the VBox into a scroll box. There is nothing magical here. But let's look inside here. You'll see two other benefits of constraints and events. One is that, well, here is one annotation. The text from here comes here, and this is the box that displays the annotations. Here is the height and y. Now, what do I do when I want to make the annotation active? Normally, I would need to come here and say, OK, when there is a mouse click on that box, I need to somehow send the message somewhere and adjust the time. In event-driven programming or even in data flow, you typically need to go to some central repository and send the time. And then the time would come back and say, oh, OK, now we have new time. Let's see if this annotation, if the time is in the interval of the annotation. If yes, you make it active. If it is active, the y coordinate needs to be 0, which means this guy is centered. But I do not want to go with this event all the way to time and figure out how things will actually propagate. All I do here is I say, well, OK, if I click on the mouse, I insist that this annotation becomes active. But I don't really care about how the time is set. This will be, again, done automatically. In order for this annotation to be active, I need to change the time. But I don't worry about how. So I can influence the time or active because things are bidirectional. And it seems to be more natural, more modular to think about setting activity of an annotation rather than figuring out what time I need to set so that it becomes active. And so these bidirectional constraints occur everywhere. You saw how it can simplify events in terms of time, event handling. The coordinate system translation is everywhere. Imagine you want to map your landmarks from the map on the camera view. It's all about coordinate mapping between the map view and the camera view and the angle of the head you are looking at and so on. Scrollbox is full of bidirectional constraints. And visualization is about placing labels such that they do not overlap and look visually appealing. But current solvers are not expressive, clumsy, and other things that we need to address in the work. And there are a few other things that I didn't talk about, technically probably the most interesting ones, and I can do it if you are interested. Thank you for your time.